Hello everyone, welcome to Digital Communication Tutorials. In this video, I am going to take up the 7th numerical on detection and estimation. Let me read out the question first. Consider the following binary signals defined in terms of orthonormal basis functions phi1 of t and phi2 of t. The first set of signals is s1 of t equals a into phi1 of t, s2 of t equals a into phi2 of t. The second set of signals are s1 of t equals a into phi1 of t, s2 of t equals minus a into phi2 of t. And the last set of signal is s1 of t equals a into phi1 of t and s2 of t equals 0. Then part A of the question says, give the signal constellation diagrams, maximum likelihood decision regions and decision functions for the 3 signal sets. And part B of the question says, give the diagram of an optimum receiver. Right, let us start with the solution part here. Let me start with part A of the question, that is to give the signal constellation, maximum likelihood decision region and decision functions for the 3 given sets. I'll start with the first set of signals here, which are s1 of t equals a into phi1 of t and s2 of t equals a into phi2 of t. Okay. From the given signal set, we can identify the coordinates of the signal vectors in the signal space as s1 equals a comma 0 and s2 equals 0 comma a. These are the coordinates of the signals in the constellation diagram. So, the constellation diagram will be given as, okay. Then we have S1 located at a comma 0. So, this will be on the x axis, this is S1 and S2 is at 0 comma a. So, this will be located here on the y axis, this is S2 0 comma a. Then we are asked to plot the decision regions and decision boundaries for the same. If you look at the diagram carefully, you will find that the 2 signal points are located at an equal distance of a on the positive x axis and the positive y axis. Therefore, assuming maximum likelihood decision, the decision boundary will be a line drawn at an angle of 45 degree in the first and third quadrant. This will be the decision boundary, right? Then all of the points that are below the decision boundary, they form the region Z1, which is decision region Z1, and all of the points above the decision boundary, they form decision region Z2. Please note, a decision region is simply a set of all points that are nearest to a vector Si than the vector Sj. In this particular case, all of the signal points that are below the decision boundary are nearer to the signal point S1 and all of the signal points above the decision boundary are nearer to the signal point S2. Therefore, the decision boundary is simply a hyperplane that passes through the origin with a slope equal to 1. Therefore, now I can write the decision boundary as, it is a straight line passing through the origin with a slope equal to plus 1. Right, this is the decision boundary for case 1. Further, coming back to the part A, you can see that we are also asked to give the decision functions for the signal set. So, let us now come back and write the received vector as x of t. Since the constellation diagram is 2-dimensional, the x of t will have 2 coordinates, let us say x1 and x2, which are given as x1 equals integral 0 to capital T x of t into phi 1 of t dt and x2 equals to integral 0 to capital T x of t into phi 2 of t dt. Therefore, the coordinates of the received signal vector will be x equals x1 comma x2. These are the coordinates of the received signal vector. Right. Now, let us move on and set the decision rule. If the received signal vector, let us say, falls in decision region Z1, then a decision will be made in favor of signal S1 of t. On the other hand, if the received signal vector falls in the decision region Z2, then a decision will be made in favor of the signal S2 of t. In a very interesting case, since the coordinates of x are x1 and x2, the received signal vector will fall in region Z1 only when x1 is greater than x2, otherwise it will fall in region Z2. Therefore, the decision rule can now be given as: choose S1 if x1 is greater than or equal to x2. If this happens, then a decision is made in favor of signal S1 of t. Otherwise, choose S2. This will be the decision rule. Okay. Please note, for the received signal point to fall in decision region 1, x1 should be greater than x2, and if x2 is greater than x1, then it will fall in decision region 2. Therefore, we have made a decision based on the values of x1 and x2. This is for the first set of signals. Let us now move on to the second set of signals. Okay. By looking at the equations for S1 of t and S2 of t, now I can write the signal vectors as S1 equals a comma 0 and S2 equals 0 comma minus a. Then I will continue for the constellation diagram. Right. Now, here the signal vector S1 of t is located at a distance of a on the x-axis. So, this is S1, which is a comma 0. Coming to signal vector S2, it is located at a distance of a, but on the negative y-axis. So, this will be S2, which is 0 comma minus a. By using the same approximation as what I have previously explained, the decision boundary will be a line with a slope minus 1. So, I will draw the decision boundary as, right. So, this will be the decision boundary. I will write the decision boundary here. This is simply a line that is passing through the origin with a slope equal to minus 1. Okay. Now, let us move on to plot the decision regions. From the constellation diagram here, by applying a very similar approximation as what we have done previously, all of the signal points that appear above the decision boundary will be called as decision region 1. It is region Z1, and all of the points that are below the decision boundary are called decision region Z2. Then, using the same approximation for the received signal vector, which is written as x of t having coordinates x1 and x2, the decision rule now will be given as. Let us come back to the constellation diagram and analyze. Whenever the signal vector x has its coordinates x1 and x2 related in a fashion where x1 is greater than or equal to minus x2, then a decision will be made in favor of signal S1 of t, and whenever x1 is less than minus of x2, then a decision will be made in favor of signal S2 of t. That will be the decision rule. So, I will write it as okay. So, that is the decision rule for the second set of signals given. Lastly, I move on to the third set given, which is S1 of t equals a into phi 1 of t and S2 of t equals 0. Therefore, the signal vectors are given by S1 is equal to A comma 0 and S2 equals 0 comma 0. Moving on to the constellation diagram. Okay, S1 is located again at a distance of A on the x-axis. So, S1 is this point and S2 is 0 comma 0. So, this is S2 which is 0 comma 0. Now, looking at the constellation diagram, the decision boundary for this set of signals will simply be a hyperplane that is drawn exactly at the midway point between S1 and S2. This is the decision boundary. Please note, we have been assuming maximum likelihood detection. So, since the signals are equiprobable, the decision regions must have equal width. And the only way we can divide the constellation diagram into two equal parts when the given signal sets are located at A comma 0 and 0 comma 0 is by plotting the decision boundary exactly at midway point between S1 and S2. So, coming to the decision regions, all of the signal points to the right of this decision boundary, they form decision region Z1. And all of the signal points that fall to the left of the decision boundary, they form decision region Z2. Okay. So, let us now write a sentence for the decision boundary of this particular signal set. As I said, decision boundary for this set of signals is a line parallel to the y-axis, which is phi 2 axis, and that passes through a point which is equal to A divided by 2, because that is the midway point here. So, the location of this point is A by 2 comma 0 on the phi 1 axis. So, I can say the decision boundary is a line parallel to the phi 2 axis and passing through the point A by 2 comma 0 on the phi 1 axis. Right. Now, coming to the decision rule. The decision rule is very simple here. Given the received signal vector x with coordinates x1 and x2, signal S1 of t will be chosen if the coordinate x1 is greater than or equal to A by 2. Otherwise, choose signal S2 of t. Please remember, we will not be using the coordinate x2 to make a decision here, because the signals S1 and S2 are both located on the phi 1 axis itself. Therefore, the decision rule will be choose S1 of t if x1 is greater than or equal to A by 2, otherwise choose S2. Right. So, that completes the part A of the numerical, which was to plot the constellation diagrams, find the decision boundaries and the decision functions for the three given signal sets. Let us now move on to the part B of the numerical, which is to draw the optimum receiver. We know that there are two optimum receivers. The first one is the correlation receiver, then we have the matched filter receiver. Since every signal set we are given here has two signals, then the optimum receiver will have two branches of either the correlation receiver or the matched filter receiver. For this particular numerical, I will be using the detector of the correlation receiver. Let me plot that. Okay. So, the input to the receiver is equal to x of t, and x of t is then fed to the two branches of the correlation receiver, and each correlation receiver, you must note, has a multiplier and an integrator. Right. It is also essential to note that the upper multiplier should be provided with the first basis function, which is phi 1 of t, and the lower multiplier should be provided with phi 2 of t. Then the product of each branch is given to the integrator. Output of the integrator is sampled here, Please note it is sampled at t is equals to capital T. The output of the upper sampling branch is the coefficient x1 and that of the lower sampling branch is x2. These coefficients are then fed to a decision device and the output of the decision device is either S1 or S2. This is the diagram for the optimum receiver. Please note the decision device will use the decision rule that is defined for each set of signals individually. For example, for the third set of signals, if x1 is greater than or equal to a by 2, then a decision will be made in favor of signal S1 of t. Otherwise, a decision will be made in favor of S2 of t. That is the end of this numerical. Well, if you like this video, kindly like and share this video and subscribe to my channel for more information on digital communication. Thank you for watching. Have a good day.